recording, and then we go to the full screen. Okay, so what we want to do today is to continue the idea about the problem of how to describe states which are mixed, right? Because we've been spending so much time talking about quantum states, and then we kind of almost forgetting the fact that just like in normal everyday life, we can also mix things in a statistical way, right? Like 3 red color marbles with orange blue color marbles mixed together, random choice. That one is nothing to do with quantum mechanics, it's just pure probability. And this thing can happen for quantum systems as well, right? So if we, most of the time we are talking about pure states, right? Pure states are represented by vectors, okay, which we will call kets. We have been calling kets in Hilbert space. Wow, okay, hang on, I ran out of ink. Okay. Yeah, so they are called kets in Hilbert space, and we use this symbol, right? So this is that object that is in Hilbert space. So this is nothing new, right? Just reviewing what we have already know. So to get the corresponding density matrix, wait, hello, can everyone hear me? I hear, can okay. Sorry, I heard the sound that we got disconnected, so I don't know what happened. Okay, good. Do you guys hear it? You know the Microsoft Teams sound that got when the end call sound, it suddenly happened, but I think, okay, so if you can hear, then things, right? It's always a pattern, it's always Monday, something wrong is gonna happen. Something weird is gonna happen on Monday. But let's try to push, I'll try to push forward. So the corresponding density matrix we have described for this case is given by, we take the ket bra, right? So ket bra is because if you bra-ket, if you multiply, you get a number. If you ket bra, you do it the other way around, you get an operator, right? And sometimes you guys have been wondering about this. If you have learned about this in other branches in mathematics, we call this the outer product. So this is the ket bra, right? And then we learn how to calculate the trace, right? So the trace of an object, we do this, right? So any ket bra, right? You just do it like this, right? So it becomes a number. So the trace is the ket bra was multiplying in the wrong direction. So the trace is to make it back to the correct direction. So you got this result over here, right? And then the trace the trace property is linear. So the trace of A times an operator plus B times another operator B, right? It's just A trace A plus B trace B. And then it is a cyclic property. So that means if I have 3 operators multiplied together, can hear? Okay, good. So everything sounds good so far. So if I three operators multiply together, what will be the trace? So this one is not really quantum mechanics, but it's very general, meaning that in linear algebra also you got this result, right? So the cyclic property of the trace and so on and so forth. Okay. So now we know, now we have introduced this kind of object. The reason why we want to do this is to describe the mixing of states, right? So now what we can do, we know how to do it for pure states, but pure states we already know. The main point of doing this is we figure out how to describe mixed states. Okay, so how do we describe mixed states? Okay, so that means let's say I have one state, okay, one state, maybe this one is pure, so let's start with a pure state over here. right? So that means if I get a pure state, it's going to be the ket bra. It becomes an operator, right? And let's say I have another pure state, right? So I row 2, and then this will be the ket bra of this corresponding pure state. And then if I do the Stern-Gallac experiment, I mix the two beams like this. And like I said, the mixing doesn't necessarily have to be a quantum effect, right? It's just a normal mixing. That means you can control how much you mix the proportion, or it's not to say that you can control, but it's just a normal effect, right? That means, let's say this beam consists of this much beam and this beam is this much, right? So if W1 is higher than W2, it means that W1 has more atoms inside. Then W2 is more thin or less dense or whatever, right? So if you mix this together, then what you have is the mixed state, and I can describe the total mixed state by the portion of the beam 1 plus the portion of beam 2. Okay, so this W is what we call the weights, or it is the proportion of mixing. Okay, so if these two are pure states described by this, then we got this description. We just substitute our original expression for row 1 and row 2. So this one is how we can describe a mixture, right? So how do we find the well, what are the properties of these states? We want to calculate the expectation values, right? So let's say I got an observable, right? So if I measure this observable A, right, maybe it could be the sigma z or whatever, but let's say any operator, what is the expectation value? So the expectation value of any observable, right, is what? So like I said, that normally we have been doing always the sigma z, but we started to consider sigma y or x, or maybe some other thing like the Hamiltonian itself. We want to measure the energy or whatever, right? So what is the expectation value? So we have found that to calculate and the expectation value, we do this formula, right? So we trace of A times rho. Okay, so trace of A times rho. So this was one of the things that we I forgot to say here, right? So this is the formula to calculate the expectation value. And how do you work this out? Well, just plug this in directly and let's see what we get. So this is the A operating on multiplied with this operator, so psi, right? And W2 phi. So the trace operation is linear. So that means what we get is the constants I can take out, and then the sum I can split into 2. So what I have here is A times this, taking the trace of this, and then W2 trace of A times this state now. Okay, and by the definition of the trace, right, so this is a ket, this is a bra, right? So I got a ket and I got a bra in the wrong order. The trace just means you do it like this, right? So you just need to do this operation for the trace, and what you found is basically just like this, right? So this is just the expectation value of A in your normal quantum state, but the state is psi, right? And then same story happening over here, right? So this is a ket, right? So I got a ket here, and then I got a bra, right? So I got a bra and a ket here in the outer product form. So the trace operation is you do this, right? So what you get here is phi A phi. Okay, so yeah, so basically what you got here is the expectation of the operator A, but when we were doing the quantum state phi alone, right? So this is a quantum state by itself. It has its own expectation value. This is another quantum state. It has its own expectation value, all right? But if you mix them together, what is the resultant? So the resultant is just the is basically what we got here is we have found is W1 times this plus W times this, right? So it's like a statistical weight. What we have here is the W over 100%, right, of the atoms in the beam gives the expectation value that is like this. Corresponding to the state, well, this one is a pure state psi, and the same story here. For here, what we got is, this is the W1%, so this is W2% of atoms corresponding to the state. Yeah, same words, to the state phi. Okay, so maybe I hope what you guys are feeling right now is, when you see this, oh, new things, so complicated, like a lot of new things to learn. But at the end of the day, it's just like, yeah, like everyday life. If you mix this many things and then this many things, then if you mix them together, what if you just choose one, what are the chances of getting either one of the choices? So the choices are like this, right? So to hammer down the point even further, let me draw the picture, right? So this one is just an everyday statistical mixing. So let's say I got the quantum state, right? I'm preparing the atoms like this, okay? So just to tell you that the atoms are different, let me draw the picture of these atoms. So they look like this, and then I have another state. So all these atoms are looking like this, right? And then if I mix them together, so this one themselves, they could be a quantum superposition, right? So this state could be like the cat is either dead nor alive. This one, yeah, that one is quantum. Same story for here. Maybe it's a definite state, maybe it's just the alive normal cat, or maybe it's a superposition of dead and alive. We don't know, right? Or not to say don't know, but it depends on the problem. We can calculate all both cases. So if we mix them together, right, it just means that we are doing this, okay? So you just put the beam of atoms together, and what we find here is basically the two beams mixed together, right? So if you do the measurement A, then what is the expectation value, what are the probabilities, then so the result will depend on the statistics of your quantum superposition, and also depends on the statistical distribution of your normal mixing. Okay, so so this is why, like, I give the example. This is like the normal mixing of things, like your coffee mixed with sugar and the water you mix together. Nothing quantum about it. So it can happen here as well. But you can also do the mixing of quantum states in this form, right? So we have shown this detail in two states, in two mixing of two quantum states, but you can definitely mix more than two combination, right? It's any number that you want. So generally, a mixture of n states, right? So let's say I got state number 1 and then state number 2 and then n different quantum states, right? So let's say we started with pure states, then my mixing of these together will be starting, the summation is let's say j from 1 to n of the weight of jj, right? So all these are states that you can mix together, and wj is a proportion of mixing. So this is how we I guess now we know how to describe the mixed state. So is generally written in this form. Right, so this is the proportion of mixing. Now the thing to realize about the W, right, is we unlearn something we learned last time. When we were doing pure states, right, when we are doing pure states, okay, so we are summing over k from 1 to n, let's say ck, and then I don't know, whatever basis you are using, right? So for pure states, these are complex numbers. But right now what we are doing is the ordinary statistical mixing. So now they are actually real numbers. So so wj are real numbers, and they, of course, they're real numbers, and this is like the statistics. I keep referring back to that because it's basically the same thing over here. So in probability and statistics, your probability values again sum to 1, right? So they obey this condition. That means W1 plus W2 plus everybody until Wn should be equals to 1, right? So it's actually like we are kind of like coming back to an easier situation, because when we're doing quantum states, when these are complex numbers, you need to do a complex conjugate and absolute value to make sure they sum to 1, and then you do normalization, right? So all these are like extra things for those who are already familiar with statistics. This one is like, oh, come back to the original probability and statistics case. Okay, so yeah, so basically that is the essential thing. So does the question give the W? Usually yes, right? So if you're asking in terms of exam question, yeah, so usually it depends how we ask the question, right? Because maybe they give you this and then calculate the result, right? Or maybe they give you the result and calculate this, okay? But that is like exam question. But in practice, the W is determined by the physical situation. In fact, there is a case of W I will show you soon after this. Once I finish talking about this, is something you already learned before, the thermal physics. Okay, but we'll come back to that soon. But let's talk about this first, right? So we got this already, and just to finish off our line of thought over here, to figure out the probability to get state, let's say some specific state number, so I get state I is given by what? So probability, it is the quantum state I is equals to, well, you do this operation. So because yeah, so it's I rho I. Okay, so the reason why we do this is because if you do I rho I, right, if you calculate out Wj, J, and then you multiply with the I, right? So this thing here will multiply together, and then you see what happens. Maybe you can already see. Hopefully you are used to this by now. This is the delta Ji, right? So the delta Ji means every term is 0 except when j is equals to this I. Let's say I is some specific examples. Let's say I is 3, right? So if I is 3, then only the third number is non-zero. So only the third number will be non-zero. So what you get here is I, and then usually we consider normalized basis vector. So it's there's a Wj, which I forgot, Wj. So we got the probability of getting this in Wj. And since we are familiar, we are using the operator notation now. This is actually equivalent to the trace of II of rho, right? So yeah, so same thing over here, or equivalently, right? So you can write this or you write this, doesn't matter, because if you write this, then when you work it out, you still get the same result anyway. Okay, so any other questions so far? Okay, so now let us understand this a little bit further, because we are introducing a new object, so we should really get to know this density matrix a little bit more. Let's look at the properties that is satisfied by this. Okay, so this is let us list down the properties of the density matrix. Okay, some textbook calls this the statistical operator. So if you read the textbook by Englert, he never calls it density matrix anywhere, because he doesn't like this term, and which is kind of true. Statistical operator is a more accurate name because it is an operator and it tells us the statistical properties about it, because we are doing the statistical mixing. Density matrix, that the word density is partially related to the probability density function, right? So it's not like the physical density or anything. And the matrix is common to the example that we consider, like a Hilbert space for the Stern-Gala experiment, so you get 2 by 2 matrix, but it doesn't have to be a matrix. Maybe it's an infinite size matrix, like for continuous variables. Then and the general case, we call this an operator, right? So this is just the naming convention, but just to keep in mind, if you read some textbooks, different people might call it different name. Quantum mechanics is still new compared to like Newtonian mechanics, so the words and terminologies, not all of them have been properly fixed yet. But the first property is this. Firstly is positivity. Okay, and the reason is because, right, the Wi, these are the weights. That means the weights of mixing, when you pick it up, it becomes the probability, right? So it's because of this, right? It is a probability. So it must be positive. So the result that you get must be positive. So we got, so this one is some specific I. So generally, instead of I, we write the symbol psi for any state in Hilbert space. Must be positive, right? Maybe if you change a basis, you this one, let's say, is eigenstate of the sigma z, but if you are using the sigma y operator, then you change to another basis. So that means if just because you change the basis doesn't, you still get a probability distribution, right? So the result should still be a positive number. So we conclude that the bra-ket of any state, if you close into your density matrix, it should be positive for any state. Psi. Okay. Some textbooks, instead of writing this full statement, they just write this for simplicity. Okay, so sometimes we see this word. What does it mean by operator greater than 0? It just means this, right? Because operator is an operator, sometimes it's a matrix. 0 is a number. But what this means is when an operator is positive, it means this. Okay. Secondly, it must have unit trace. Second property. Excuse me. Okay. So in the general form, the reason why it has unit trace, right? Let's look at the general form. So for an arbitrary basis, we got summation of j of the weights j, summing over the corresponding ket bra, right? We are mixing different states. So the unit trace means the trace must be equals to 1. Let's find out. What is the trace of rho? So the trace of rho is the trace of this thing. Okay. And the trace of this thing is, you can put the trace inside. Right? So how come taking the trace is equivalent to this? Is the reason is because the trace is linear. Right? So for the two terms I have shown you already, let me remind you, right? Trace of something plus something, I can separate this out, right? So for any summation, any number, I do the same thing. So this is the trace. And then what do you do when you trace this? So I got a bra and I got a ket. So the trace is, you shift it and you put it back here. So basically what this means is this becomes the summation over j, bra-ket j. So this is just 1 again. So this is basically summing over j of wj. And because wj, these are the weights, right? They should sum equals to 1. So so this is equals to 1. So what we conclude is trace of rho should be equals to 1. Okay. So that is the trace. And the density matrix should also be Hermitian. Okay. The reason is because if I take any ket bra by itself, right, the same ket and the same ket, you do the bra and you do this. If you do the dagger, they are identical, right? So you just flip it, they become the same thing. So if you do this to your general density matrix, then if you do the dagger, right, is basically, yeah, taking the dagger of everyone, you just end up with the same thing again. right? So in other words, rho dagger is equals to rho. So this is the density matrix is Hermitian. Okay, and so now that we have the density matrix, right, it is supposed to be something that can describe pure states as well as quantum states at the same time, right? Or the whole thing is called rho in this general form. But we should still be able to tell the difference between a pure and a mixed state. So this is one way to identify a pure state. So how do we identify a pure state? So it goes like this, okay? Like I said, right, the mixing is creating a state where I got the weight 1 E1, or just write 1, right, and then plus the weight 2 2 so this is a mixing of various different states. So if I'm talking about a pure state, it means no mixing. So that means there's only one term. So only one term, that means it's just psi. Right, so that is what we started with, right? So this is we get our concept of a mixed state is, let's say, okay, we are familiar with quantum states, so we got different possible quantum states, and then we mixing by adding them up. So if there's only one term, that means you're not doing any mixing, so it's only one term. And if there's only one term, what happens if you square this? Let's find out. Okay, so if you do this one term, then this thing just multiply by itself. So a state should be normalized, it should be equal to 1, right? And if you this, you just come back to the this thing again. So for the pure states, they obey this identity. So if you square a pure state, not identity, you recover the same state again. So if you square a pure state, you got this. Okay, so this is what you get when you do a pure states. Okay, so does that mean that if it's a non-pure state, I square this, I may not get this? That is true, right? So this is the next point. What about non-pure states? Okay, so for non-pure states, right, is when rho square is not equals to rho. Okay, so in fact, let's find out, right? So for non-pure, there's mixing. So if there's mixing, means I got rho is equals to W1 1 1, W2 2 2, and so on and so forth, right? So mixing means I got more than one term. Right, so let's just write this as a summation over j, wj, jj. Okay, and let's find out what happens when we square this. So squaring this means summation multiplied by itself. So when you multiply multiple summation, right, usually we should change the symbol. So let's say this is I, right, and then let's multiply them together. So I'm summing over j, and then I'm summing over I. When you multiply them, is wj wi. Okay, and then I got j times I, and this one is the delta ji, Kronecker delta, right? So this, let's say if I sum over I, right? So if I'm summing over I, this term is only non-zero only when I is equal to j. So that means when you sum this over, I'm left behind with w, and then all the I change to j. Okay, so definitely this is a w square over j. So this is not equals to the original state, right? So this is not equals to the original rho, and in fact this is the wj. So we notice that, right, in fact we observe that the trace of rho square is going to be what? So it's just the summation of wj square, and if it's non-pure, it's going to be less than 1 for non-pure. Right? Can you see? Okay, because the W are the weights, so they should sum up to 1. So if I square them, it should be less than equals to 1, right? In fact, it must be strictly less than 1 if n is greater than 1, right? If I more than one term, so if w1 is if it's just one term, then w1 equals to 1, so w square is still equals to 1. But if I multiple terms, right, that means all these are real numbers, so all the real numbers summing to 1 means everybody must be less than 1, right? And they cannot be negative because these are probabilities. So everybody less than 1, that means if I square them, it becomes something even smaller. Then if I add them, it will be smaller than the previous result. Okay, so that is our so this is our property of the if you get a non-pure state, right, a mixed state, then this is what you get. Okay. Hermitian not closed in addition. What do you mean? Hermitian operators are not closed in addition, or the Hermitian it is closed. It is closed, right? Because if you take the set of Hermitian operators, right, and then if you add the two Hermitian operators together, you still get an operator that is still Hermitian. So therefore, Hermitian operators are closed in addition. Okay, I think that's correct. I will let you know if I'm wrong later. I need to double check. I haven't been thinking about this for a while. But it should be closed under operation. If you take the set of Hermitian operators, the space of Hermitian operators. Okay, so for your for the other question about the W's, are they given in the question? Yes, is in the non-exam setting, right? Where does the W come from? It depends on what kind of system that you are considering. Okay, so now I guess now is a good chance. What time is it? Let's check the time. Now is a good chance to tie together a few concepts that you have been learning in your year 1. What I'm talking about here is statistical mechanics. Okay, we put a thing quantum there, but actually statistical mechanics by itself has already a few examples from quantum mechanics, right? When you are doing the thermophysics, you have already calculated the two-state system, right? It's just that we didn't call it the two-state system back then. You haven't learned all this stuff yet, right? And also, in fact, you might have already calculated the entropy of a harmonic oscillator and things like that, right? So this is how we tie. Now we can tie together the concepts. Okay, so let's say, right, for statistical mechanics, we need to start with a few assumptions, but they are like kind of like pretty common situations. What I'm saying here is that, let's say in a statistical mechanical system, it will be described by an Hamiltonian, as everything else is, and let's say we know the eigenstates. Okay, so it is an assumption, but it is a slightly non-trivial assumption, because if you recall the previous chapter, finding eigenstates of Hamiltonian is actually not an easy job, right? So let the system be governed or described by a Hamiltonian H, and the eigenstates Ej. Okay, so that means if I know the eigenstates, whatever this is, if I multiply the Hamiltonian into it, it will just give me back a number which is the eigenvalue corresponding to the energy level, right? And let me say, just assume, right, just to make it easy to imagine, I got n energy levels to the system. It could go all the way to infinity, like n could be finite or infinite, right? So what distinguishes a system with a quantum system with a statistical mechanical system? So these are the two different settings. In a quantum system, right, we need to isolate this from the environment, okay? Because remember, like the cat example, still the cat. The point of the cat being in a quantum superposition is we do not observe it, right? So once we observe it, we kind of expose this to the environment, and the words that we use is we lose the coherence. Okay, so the quantum superposition is gone when you open the box and you make an observation, right? So in order to make sure your quantum state remains a quantum, right, the quantum properties, to remain it like this, you need to isolate this from everything else. So it must be in vacuum and everything, and so on and so forth, right? You must not disturb the state. But a thermal system, right, if you recall when you're doing thermal physics, you are describing an object usually having some temperature. That means an object in a heat bath, correct? Right, let's say a cup of water in a room having a fixed temperature. Now, the reason why this is a heat bath is because it can exchange energy. Your system that you want to study is exchanging energy with the environment. So that is a very far away from the quantum cat case, because you are exposing it to the environment, right? And so that is the main distinction. So that is a coupling between the system to the environment. So how do we describe this? So this is not quantum mechanics anymore, you would say, but still, right, if it's still a system, the energy levels are still the same, just that the probability distribution now is no longer a pure quantum state, right? But if you look at the state coupled to the heat bath, it is calculated from statistical mechanics, right? So what is the probability of observing a certain energy level for this heat bath? Okay, so this is something that you calculated in thermal physics, right? So I don't need to do this here, but the result was, it depends on what was called in by Prof. Ong. Some people call it the Boltzmann distribution, right? And some books call it the Gibbs distribution. Gibbs is because Gibbs was the first person to derive this, if I remember correctly. Okay, and it tells us the probability distribution of your corresponding eigenstate, because your thermal state, right? So your thermal state is J, Wj, and now we are expanding using this basis, right? So this will be given by the Gibbs distribution, right? So what was the Gibbs distribution or the Boltzmann distribution? Do you remember? Is exponential minus beta and the ith energy level, right? So this beta here is 1 over the Boltzmann constant times the temperature, right? So the derivation, actually this one also can be derived. It's just that the derivation doesn't depend on quantum mechanics. It applies to quantum system as well as other classical gas system as well, right? Like classical gas and all those things. And the reason why you had this distribution is by assuming that the system naturally needs to maximize the entropy disorder of the thing, right? So this is our distribution, right? But of course, you must make them, I almost forgot, you must make them sum to 1, right? So you need to have a constant. So this one is a constant. And if you remember thermal physics, those who have taken, you know what this is called. I will give them the name later. But basically what we have here is the quantum system. Well, I shouldn't say a system with energy levels are given by the eigenvalues of h. So this part is the quantum mechanics part, but it's still the system. But if you expose it to an environment in a heat bath, right, it will because it's the statistical mechanics, right? Coupling to the heat bath is a very random process. So if it's very random, what is the expected probability distribution? Then you write this as a mixed state. Right? So like I've been telling so many times, I repeated this phrase already. The mixed state is just a normal statistical or probability process. So what you get is summation 1 over z, j, and then the weights are w is given by the Boltzmann term, and then the energy levels. Okay, so this is how you got this, right? And the z is because the w's must sum to 1. Right? So the sum of j of wj must be equals to 1, and the wj was what we call 1 over z, minus beta ej must be equals to 1. So 1 over z summing this e beta ej is equals to 1. So if I bring the z over, we got this familiar formula, right? So this is what we in thermal physics, this is what we call the partition function. Right, and if you remember, the partition function is a very important quantity in thermal physics. Freshman nightmare. Yeah, so you guys have to learn all this, right? So maybe my guess is it's a nightmare because it's suddenly got a lot of new concepts, especially in the first few years. But what we are doing now, right, as you're going along in your years in first year, second year, you are learning more and more things. So now we give things a little bit more context, and then now you realize, it's actually like this, right? So we can understand something a little bit more, okay? So it is, I guess this is a natural human way to understand things. Even like if you like movies, in Star Wars, you get a prequel, so to give more context of what is happening, things like that, right? So, and then as well as sequels and then prequels, to tell the story what happens before and what happens after, and then you give us more insight on what is actually happening. Okay, so yeah, so that is one thing. Never understood year 1. Well, I guess now if we do this systematically, if you don't understand now, then now is a chance to understand it a little bit better again, right? So this is a second chance to go through this. So I guess it should be worth our effort to understand this. But right now, what I'm going to do next is more on our operator language. I can write down a thermal state as an exponential of an operator. The reason is the following, right? So let's start with this. Okay, so I want to show a thermal state can be written as the operator rho is equals to 1 over the z, right? So z is the partition function, e to the beta h. Okay, so this whole operator is given by this. Right, so remember this is the Hamiltonian, so this is an operator. And exponential of an operator, we spend quite some time to explain why this is true already. And I will show you again here. All right, the reason is because the following. We start with what we definitely know. If Hamiltonian is acting on the eigenstate, it gives you back the eigenstates with the eigenvalue. Right? Okay, so yeah, okay, and if I do this, right, so what does this mean, right? So this means the exponential of an operator means I do a series, right? So this is a series of 1 over k factorial negative beta, and this thing is to the power k. So let's see what happens if I operate this on the eigenstate ej. okay, and this is k, right? So this is 1 over k factorial. So this, let me split this out, this negative beta k, and then hk operating on this, right? So Ej is the eigenstate of h. So every time you operate the h, it gives you one eigenvalue, and then operate again, it gives you another eigenvalue. So if you operate k times, it just gives you k eigenvalues, right? So E beta h Ej is equals to the summation from k to 0 to infinity 1 over k factorial negative beta. Then this becomes a normal number, right? So this is the Taylor series of the normal number of negative e beta j, right? So I have shown you that e to the power of Ej operating on the ket Ej is the same as taking the exponential operator acting on Ej, right? So I've convinced you that this is the reason why the operator can suddenly change into this, as long as we are referring to the Ej basis. Okay, so now the mixed state that we were considering, right, with the Boltzmann distribution, is what? The mixed state is the 1 over the partition function sum over j from 0 to infinity. Well, depends on the energy level, right? So it could be infinite. We've got Ej, 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 right? And I have shown you just now that this part is a bit not rigorous, right, by mathematical standards. But I will change this into Ej, right? This is equals to this, okay? So that if I rearrange this, what happens? So notice that this, now I change this back into the operator form. So this is independent of the operator, right? So what I got is 1 over z e to the beta h. I can take this out because now is independent of the j, right? So this j is h is independent of j. Okay, so I can take it out of the summation, right? And what we have here is the summation over Ej. And what is this now? So these are eigenstates of the Hermitian operator H. That means we have proven back in chapter 1 they are complete, right? So I'm using this as a chance to refresh what we did long time ago. These are complete. Complete means what? Complete means the sum over everything should be equal to the identity, right? So it's just identity times the operator. So I got rho of this is beta h. Okay, and then from here we can get another result that because the density matrix must have unit trace. So if I trace rho, I should get 1. That means is I should trace this to get 1, right? And z is a constant. My partition function is the trace of e negative beta h. So if I bring the z over, z is just equals to the trace of e to the beta h, right? So this is an operator, right? This is an exponential of an operator. It gives you some other operator defined through the series, right? So it's still an operator, meaning that at the fundamental level, operator should eat a vector and spit out a new vector, right? So you can do matrix things to it. You take the trace, find the eigenvalues, and taking the trace of this is equivalent to getting the operator, okay? And so yeah, so we got the thermal state. So our thermal state is written as rho is equals to 1 over z e to the beta h. Okay, so the reason why this is just a short example in the lecture notes, but I'm spending quite some time to talk about this is because quite a few times already. I remember in the main campus talks in Wednesday, right? I've seen this appearing quite a few times. So hopefully next time when some other talk use this result again, then you can kind of know what this is, right? So in research, people tend to use this in the operator form. Rho. Yeah, that is because of this. The reason why trace of rho equals to 1 is the second property, right? So why does rho have a unit trace? Is because generally speaking, right, tracing rho means is the sum of probability, right? So in other words, trace rho is like summing up all probabilities. So they should sum equal to 1, right? So that's why they equal to 1. Okay, and so this is a general density matrix, right? So this is the property for the general density matrix. And then for this example, right? So this is example 7.2.2 in the lecture notes. We are talking specifically, okay, for this particular mixed state. When you're doing statistical mechanics, it is an example of a mixed state of a mixed quantum state, right? It's not pure. Like I was saying just now, the cat in the box is a pure quantum state. You're isolating from the environment. Once you observe it, the quantum superposition is lost. So it's not very quantum anymore. And if you, in a similar way, if you take a system and you couple it to a heat bath of a certain temperature, right, it becomes a mixed state. So this is how you get the information related to the mixed state, right? And now we can tie back something again from thermal physics. Okay, now that I got a mixed state, we can calculate the expectation values of operators, right? So for example, given a quantum state, we tend to calculate the expectation of energy, right? That means the operator is the Hamiltonian. So what is the expectation value of this in the thermal state? Right, so given a thermal state, let's say, in fact, you can try to work out try to think of various problems, like can I combine this in a system? Many situations can happen, right? We have found many examples of Hamiltonian before, like the Larmor precession. We wrote down the Hamiltonian. The ammonia maser is another Hamiltonian. Hydrogen atom is a bit more complicated, right? You can write it, but it's messy. Never mind. Harmonic oscillator is also another Hamiltonian. So let's say for a concrete example, right? So let's say the ammonia maser, right? We got a Hamiltonian there. And what we did was, to do the maser, we put electric field and things, but let's take out the oscillating electric field. Okay, but now let's say my ammonia atom is in a heat bath having a certain temperature, right? So it's not in vacuum anymore. You put it in a very hot box, right? You put it in an oven and then you microwave or whatever, right? So there's a temperature there, right? So the state, after a while, the state will no longer be quantum anymore. It will become this mixed state. So what is the expectation value? What is the expectation value of the energy of this system now, right? Let's say the ammonia molecule in a heat bath. So what we do, our normal operation, right? So for any operator, we trace it with our rho to find the expectation value. Okay, now let's see what happens if I do it to this state. So that means I'm tracing it with my operator times my thermal state. The thermal state is just this. But if I want to tie this to thermal physics, I need to use this form. Yeah, because I wanted to connect this to your thermal physics, right? Okay. So all these are numbers. The z is a constant, so the trace is linear, so I can take it up, right? And let's keep it like this first, but what I want to do is I multiply the h inside. So these are just numbers, so I move the h inside. So this is summation from j from 1 to n, right? So I got n energy levels. So I'm summing from 1 to n, E beta Ej, h operating on this, right? And because these are eigenstates, it just gives me Ej, right? So I got 1 over z. The trace of summing j from 1 to n is just Ej, so it's just a number now. Right? And then the trace operation is linear, so I can take this out. And then I'm taking the trace of Ej. Right? So again, the same story happens here. What do you do when you do the trace of a ket bra? Right? So I got a ket bra here, so you do the trace. That means it's just Ej, which is just 1. Right? So this term becomes 1, so I'm left behind with a summation of this. Okay, so yeah, so this is the expectation value of the energy. So this is the formula that appeared in statistical mechanics, right? Yes, so you may or may not remember this, but what I'm saying is this is the formula that you can find in your thermophysics textbook, right? That is looking like this. Okay, and also remember that z is the partition function of this, right? So I got Eje beta Ej. The partition function is also the summation over beta Ej, right? So this is equivalent to 1 over beta. The formula, right, is the same as writing the derivative of the log of z, right? So this is yeah. I think in the thermophysics textbook, I think they call this U, right? So Ej, E beta Ej. Okay, so these are important concepts, right? And this is the reason why, yes, you have learned thermophysics in year 1, you learn all these concepts. Now we learn quantum mechanics now, and these are like not two totally different things, right? So they are describing the same system, but now we are doing it from different viewpoints, right? So quantum system is quantum state, quantum superposition, things like this. But if you couple it with the environment, it tends to become a mixed state, right? And the Boltzmann distribution that we learn in year 1, right, in textbooks, right, whether in this university or other universities, basically year 1 textbooks, they have a distribution, right? And it is in the context of our quantum system, it is a mixed state with a certain probability distribution. Okay, so yeah, so I think now should be a good time to take a rest. Yeah, yeah, I know, it's like the Lon-Z formula, right? Yeah, it's called the Helmholtz. It's related to the yeah, never mind. I also can't remember exactly the definition of Helmholtz, whether or not includes the beta. In any case, let's take a break for now. So let's take 10 minutes break. So let me stop the recording. Okay, and share my screen. Yeah. No one else, right? What week are we at now? We are quite close to the end of the semester already. Okay. Oh, we are week 13. Yes. So yeah, we have only 2 more weeks left. Time is going pretty fast. So what we're going to do next is our next topic, which is, what's the chapter number? I forgot. 7.3. Yeah, we are going back to the Stern-Gallac experiment again, right? So the Stern-Gallac experiment is a very nice experiment. It's simple enough that we can it's simple enough, but it's complicated enough to get some quantum properties. So because now that we know the language of the mixed state, right? So our problem started with if we mix the two beams together, what do you measure in the Stern-Gallac experiment? So let us find out now. Okay, so this is the Stern-Gallac experiment. Part 3. Right, so this is the third time we're coming back to this experiment. Okay. Yes. So as a reminder, back when we are doing the original Stern-Gallac experiment, all the possible states are created from, this is a two-dimensional Hilbert space, right? So it is either the spin up or spin down. Okay, so this is the basic basis vectors that we have, and Wei Zheng have just shown that these are eigenvalues of sigma z. So if you want to calculate eigenvalues of sy or sigma y, then you do the transformation correspondingly, right? So this is why, yeah, Wei Zheng was warning us, which is a very important warning, that do not confuse the different eigenstates. So up y, up down z. So this one, implicitly, I'm saying the sigma z basis, right? So that one was, we are doing pure states. So we can use cats. And in the past two classes, we have shown that if we do just a normal classical mixing, statistical mixing, then we need to describe using a density matrix. Right? So this is a two-dimensional Hilbert space. So if you do the ket bra on this, we expect to get a 2 by 2 matrix. Okay, and well, if it's a 2 by 2 matrix, then let us look at the most, let us see what kind of 2 by 2 matrix we can have. The general form would be something like this. So it's a 2 by 2 matrix, so let us call this ABCD. Right, and the A, B, C, D are complex numbers. Okay, so now we ask the question, right? Just now in the examples that we have been discussing so far is like mixing one beam and two beams, and these are very specific. So what is the most general situation we can think of? So let us try to write down what are the most general Hermitian, what is the most general density matrix that is satisfying the properties, which is Hermitian, unit trace, and all those things. Okay, so we are trying to do this now. Okay, so the first thing that we notice is that since rho is a density matrix, it must satisfy the properties of being Hermitian. Right, so Hermitian means rho dagger is equals to rho. So if you do the dagger to this, you take the transpose. Right, so transpose means you flip the off diagonal terms. The diagonal remains the same. Dagger also, you must do the complex conjugate, right? And according to it being Hermitian, it must be equal to the original one. So from here, we conclude that A dagger must be equal to A, D dagger must be equal to D. So the diagonal terms must be real numbers. And then C bar equals to B, and then B bar equals to C. Okay, so that means both are the same condition. Actually, you just conjugate both sides, right? And that means, right, let me write B is a complex number. So if I write B as a complex number, is x minus iy. Okay, then if B is equals to this, then C must be equals to the complex conjugate, so it's just plus iy, right? So here x and y are real numbers. Okay, so if you conjugate, you don't do anything to it. Is the real number is the same. You only conjugate the I. Okay, so we are narrowing down what are the possible entries of the density matrix. Okay, so this is the first property it must satisfy. Second property is it must be unit trace. Okay, so you were asking why the trace must be 1, because it's a sum of probability. So the same thing is happening here. Trace of rho is equals to 1, but now trace of rho, if I write this explicitly, is just equals to A plus D. And they are, we know that they are real numbers. Okay, so if the trace must be equals to 1, then there's only one free parameter on this equation, right? Free parameter, kind of like relating to the degree of freedom. But so if this is equals to 1, then let me purposely write as 1/2 plus z as A, and D is half minus z. So whatever this z is, the trace will be equals to 1. So z is a free parameter here. Okay, so from here we conclude that A must be half plus z. So z must be another real number. So half plus z. D is half minus z. And then just now we said that B was x minus iy. C is equals to x plus iy. Okay, so let us update our knowledge that we have. We are kind of like constraining the possible values of A, B, C, D already, right? So A is half plus z, B is x minus iy, C is x plus iy, and then this is half minus z. See, if you trace it, you get half plus half is 1, and then the dagger is equals to the same thing. The complex conjugate equals to itself. So the cool thing happens if I split out the free parameters, right? So what we have here is x, y, and z. They are real numbers, and they are independent parameters. So a cool thing happens if I split out the independent parameters. So this one is actually, if I split this out, first we notice that this is half plus half, and then the x are here, so this is 0, x, 0, and then this is 0 minus iy, 0, and then this is z, 0, 0 minus z. So can you recognize something familiar? Okay, so you see something familiar. This is something like the Pauli matrices, right? And this is half times the identity. If I take out the x out, I got this. If I take the y out, I got this. If I take the z out, I got this. And then suddenly the Pauli matrices appear again. Right, so what we have found is that the density matrix that needs to satisfy these two properties is actually can be constructed using the Pauli matrices. So it's just half identity, and then this is x sigma x plus y sigma y plus z sigma z. Sometimes it is convenient to write as a dot product. This one looks like a dot product of a vector r, dot product with the sigma. Okay, so so where r is equals to just xi plus yj plus z case, right? Something we are familiar with. Sigma z is the way of writing sigma I, sigma y, sigma zk. Okay. Okay, so I guess to illustrate what is going on, right? Let us do a quick example. We are not finished. The R can be constrained even further, but let us kind of like explore how this works by looking at an example. So let's look at 7.3.1. We got a SG experiment consists of the beam in this pure state, right? Something happened. Yeah. So I forgot to say something, because you guys haven't learned the trace. Someone mentioned last time trace of a matrix. right? So if I take a trace of A, B, C, D, right? Trace means you do this. Okay, so yeah, even if it's a 3 by 3 or 3 by 3, well, A11, A12, A13, A21, A22, A23, A31, A32, A33. Trace means you do this. Is A11 plus A22 plus A33. Right, so that is what it means by the trace. Yeah, so we were doing example 7.3.1, right? Our state initially is the up. So again, every time when I don't write the Z means it's the sigma Z direction here. So what the first part is just to find the corresponding density matrix, right? So the density matrix is like this. Okay, so no problem here. This part is very easy because if you go back to your usual matrix form, in the basis it's just 1 0, right? So it just means 1 0, and then dagger is 0 1. Everyone here are real numbers, so this is 1 0 0 1 if you multiply out the matrix. But if I want to express in terms of what we got just now, right? So if I express in terms of this form, right? So what we have found is, well, let me purposely write it in this way. So this first term is this is 0, right? 0 times 0 0. So the first term, let me purposely write, I want to, the first step is, I guess what we can try to do is to isolate the I out, right? So I got half I, okay? And in order to make sure this equation is satisfied, I plus half here and I minus half here, and the other two is 0. So what we got here is half 0 1, and then plus half 1 0 0 minus 1. So this is the half identity plus half sigma Z. So this is the density matrix in this form. Okay, so this is now how we can try to describe the Stern-Gala experiment using the density matrix. And then the second part of this example is asking us to find the expectation value in the sigma direction, right? So we have done this. This is the most basic case we done back in chapter 2. But now using the operator language, we are supposed to do the trace of sigma Z of rho. Okay, so sigma Z of rho just means that I need to do the trace operation of sigma Z, and this is half identity plus half sigma Z. So firstly, let us multiply the sigma Z inside. So I got half sigma Z plus half sigma Z square. Do you remember what is sigma Z square? Polymetric square is back to the identity. So trace of half sigma Z plus half of the identity. So half trace of sigma Z plus half trace of the identity. Okay, so what's the answer here? The answer is 1, right? So I think you guys are not familiar with this. I kind of assume you guys know, but actually you guys didn't learn this in linear algebra, is it? So now that I know, let's do this carefully. Okay, so polymatrix seems to have 0 trace. Trace of this is 2, right? So it's 0 plus half times 2, so the expectation value of this state is 1. Okay, what was the state that we started with? The state is the up Z, right? So plus 1, so the expectation is a definite state, so the expectation value is corresponding to the eigenvalue. Then the third section is part C. I want to find now the expectation value of sigma x, so the x direction. So I need to trace this, right? So tracing this means sigma x times my rho was half I plus half sigma Z. Okay, so that means I need to trace half sigma x plus half sigma x sigma y. Okay, so I need to do half trace sigma x plus half trace of sigma x sigma y. Hang on, Z. This is Z. Okay, so what is the first term? So the first term is trace of sigma x is just 0, 1, 1, 0. So the first term is 0. And what is this now? Do you remember? So we are using the cyclic property, right? So sigma y, sigma z is I sigma z, right? So if I change, if I do the cyclic, that means sigma y, sigma z is I sigma x. Therefore, sigma z, sigma x is I sigma y. See, I can't remember. I need to start from the beginning. But this is flipped. So if I flip this, is negative I sigma y. Okay, so this is negative I sigma y. Right, so this is I over 2. Trace of sigma y is also 0 because 0 plus 0. So the answer here is 0. Yeah, basically yes. So if you have a density matrix, it will be infinite series. Yeah, I because I mentioned it once and then I went too fast. So because it's important to remember when introducing new concept, right? Must mention it like a few more times to let it settle down the brain. Yeah, there's a GE linear algebra if you want to take like for those who are interested. But I guess probably this is one thing about learning physics is sometimes you learn the math and then because we don't understand how is it being used, so it's not easy to remember a lot of things. And then now that you've taken second year quantum mechanics and then things like that where the linear algebra is used a lot, and then if you go back and see through the linear algebra stuff again, then it's like, okay, now it's like this, right? So it's like the prequel type of issue things. Okay, so the other aspect, we have not much time left. So we shall start talking about this probably halfway. And we will have to continue next class. 13, 14, 15, yeah. Okay, so let's talk about this. Because now we are gathering more and more tools already. So we know what are the Pauli matrices and what do they mean. They are just h bar over 2 time related to the angular momentum operator of a spin half particle. Now we have also learned the density matrix. We can describe mixed states. And this is another advantage of using a density matrix. Whether it's a pure or mixed state, right? We can now measure the possible outcomes where the magnet can be in any direction. Because last time our knowledge is quite limited. We are only fixed at x, y, or z directions. Only 3 specific directions. How about the diagonal 45 degrees magnet? What will be the experimental outcomes? We haven't learned how to do that yet, but now we can do this. Okay, so to remind you, last time when we were measuring the x component of the spin angular momentum, which is basically h bar over 2 of the Pauli matrix, right? So it is the same as measuring I dot this, so it's basically Sx, right? Or it's just h bar over 2 sigma x. Okay, so if I want to measure the x component of this, I do sigma x. So if I want to measure the y component, right? So same thing, you measure the y component, you dot product with this, so you get sy, and therefore it's just h bar 2 sigma y. And then same thing for the z component, right? You measure k in the s direction, so you got sigma z sigma over 2 sigma z, h bar over 2 sigma z. Okay, so so this one means the magnet also must be pointing in this direction, right? So these are done by setting the SG magnet exactly in the X, Y, Z direction only. So that is kind of fixed, right? Sigma Z, sigma Y, sigma X. But what if the magnet can be in any orientation, right? What will happen to the experiment? Okay, so that is the question that we want to address now. So what if the SG magnet is in an arbitrary direction, right? So suddenly it's getting dark. Yeah, so what was my magnet? So let's say my magnet is some weird direction, right? So this is my SG magnet. Right? So my direction of this is some n direction. Okay? So what happens to your spin? Okay? So what comes out? Or what are the probabilities? How do you even calculate this? How do you write the state? Right? So what is the eigenstate of this magnet, in fact? Right? So if the so n is the unit vector describing the direction of the magnet. So it's kind of a simple generalization, because actually if you think about it, if you orient it in a different direction, it's just an orientation. So if you want to measure, that means it's just a matter of how you point the vector. If I wanted to do x direction, I take the unit vector in the x, I dot with my vector. If I do y, I take the y vector, I dot this. So if I want to measure some other direction, I will take this unit vector, then I measure this unit vector dot product with my angular momentum vector. So that is kind of the simple answer here at the moment, right? So it's basically h bar over 2 n dot sigma. Okay. But the not so simple question now is, we want to ask is, what is the expectation value? I want to get a formula for any n and any pure or mixed state rho. Okay, so now we are starting to get greedy already, because remember how far we are coming, right? When we started in chapter 2, we only got the Z magnet in the Z direction, right? And then the state is a pure state, and then we got this. We learn how to calculate probabilities. Then after we learn about angular momentum and spin, oh, we can point the magnet in the x and y direction as well. We got all the possible eigenvalues and things like that. But right now, we know mixed state, so I can mix the beam. And then the magnet, I point in any direction. So what will I get? Okay, so now we should be able to describe almost every possible situation that we have over here. But we have 2 minutes left. So let's just calculate for 2 minutes, and then we just continue until on next Thursday. The first thing that we want to do is, if we want to calculate the outcomes, the first thing that I want to do is to get the eigenvalues. Okay, so that means I need to know the eigenvalue of an arbitrary sigma z, right? So I guess I can only list down until here. The n vector is nxi plus nyj plus nzk, right? It's just telling us the direction of the state. So if this is a unit vector, so that means nx squared plus ny squared plus nz squared should be equal to 1, right? It's just a vector of length 1, and then sigma this is just sigma xi, sigma yj, sigma zk, right? So if I do n dot sigma, that means I got nx times sigma x. What was sigma x? 0, 1, 1, 0. And then ny times sigma y. and then nz times sigma z. So 1, 0, 0 minus 1. That means I got in matrix form. This is nz. This is nx minusiny, and then this is negative nz down here, and then this is nx plus iny. Plus is the conjugate of the other one. Okay, so yes, the methods we are quite familiar by now. So maybe in between today and Thursday, I guess what you can do is to see if you can calculate for yourself. The first thing that we want to do is to get the eigens, to get the eigenstates, right? We need to get the eigenvalues, and then we get the eigenstates of this. Okay, so we don't have time to do this now, so we'll continue this on Thursday. So you can calculate this for yourself, and when I do it on Thursday, you can compare whether you got it right or not. Okay, so yeah, so I guess that's all for today. No more time, and let's stop the recording and we continue on Thursday. Okay.